as I mentioned before, the derivative is a measure of a rate of change. Okay. So how one quantity changes with respect to another. Now, in the physical world, a lot of times that quantity is time, how something changes with respect to time, because we're interested to make predictions about the future, the weather, the orbit of comets, or whatever. But we like to investigate how things are changing and from that make predictions about the future. Now, if we could draw the graph, then the steeper the graph, the faster the quantity changes. Okay. So I've got 3 graphs here. So say we were looking at this particular point P. Now we know at that point, the derivative, remember, measures the slope of the tangent. So therefore, it's positive. So that's when we know, okay, our rate of change, the function is increasing. Okay, so the function value must be increasing at that point. If I was right at the top there, then I'd get a horizontal tangent, the derivative would be 0. So the rate of change is 0. Well, if there's no rate of change, we say it's stationary. It's not going up, it's not going down. It's stationary at that point. And the third situation would be, say, R over here, where when I draw in the tangent, we can see it has a negative slope, and that's when we're going down. So consequently, we say, well, the function's decreasing at that particular point. So there's sorts of things we're interested in. We want to know when functions are increasing, when they're stationary, when they're decreasing. Now, there's point P and Q. We can see the slope of the secant PQ at that time. If I want to find an average rate of change, rather than using the derivative, I would simply draw the secant between the 2 points I'm investigating. Now that's the difference between the average rate and the instantaneous rate. So PQ, the slope of that line, gives me the average rate of change from P to Q, where at R, that slope gives us the instantaneous rate of change. And in reality, that's probably what we're more interested in. I mean, imagine you're driving in your car. You want to know how fast you're going at that particular instant. You're not interested in knowing, I wonder what my average speed was for the last half hour. I mean, it's not useful information. So we've got a water tank that's being emptied. Quantity Q litres of water remaining in the tank is given by this particular function there, if they were to plot us. At what rate is the tank being emptied at any time t? So we're going to come up with a formula, some general solution to this problem. Well, if Q is 1,020 minus t squared, the rate of change of Q with respect to time is dq to t. So I'll differentiate Q with respect to time. I've got to use a chain rule for that, bring down the power, lower the power, diff the inside. But it will be changing at negative 20,000, I was going to say then, negative 2,000 times 20 minus t litres per minute. So all right then, the next logical question is, well, if that's the rate that it's changing at, how long is it going to take to empty the tank altogether? Well, I know the tank's going to be empty when Q equals 0. So I go back to the original function for that one. And okay, 20. It's going to take 20 minutes to empty our tank. So we want to know the instant the water's flowing out of it at 20,000 litres per minute. We might need to know that there might be some, I don't know, bit of machinery that can only handle so many litres per minute flow. And so they want to know when does it get to that point? When is it flowing out at a rate of 20,000 litres per minute? Well, that's when we'd use the derivative. We want to know when the derivative is negative 20,000. So we'd solve that, and that's when t equals 10. Notice I set the derivative at negative 20,000, not 20,000. Because negative implies decreasing, it's going down. So if it's flowing out, that volume is decreasing. So I want a negative. Right, so now they might say, well, look, over the first 5 minutes, what is the average rate? Well, if it's the average, then I'll need to know how much was in there when t equals 0, and we get 400,000 when we sub into Q. How much is in there at t equals 5? And we'll work out the average rate from that. So 225,000 minus 400,000 divided by 5 minus 0. So on average, see, I notice I've got a negative rate. So now on average it's emptying at a rate of 35,000 litres per minute. One of the really useful things, my calculus I guess was first thought of, was to study motion, how fast things are moving and things like that. So our equations of motion. Okay. Now this whole idea of calculus, I'll give a little bit of a history lesson here. Calculus was discovered. Notice it was discovered. It was not invented. You don't invent maths or science. You discover it. Because from a mathematician or a scientist's point of view, it's always existed. It's just up to us to discover it. The first bloke was a German fellow, Gottfried Leibniz, or Leibniz, not sure how you say that, was 28 years old when he came up with his idea. Now, it's actually his notations that we tend to use in modern times now for calculus. The long S symbol for integral, which we'll see later, was his. And the other one, who you've probably heard of, was good old Isaac Newton. He was around 1665, he was working on this, and that was when he was 22. Now, he used calculus to explain the laws of motion, and when we deal with motion, we often use what's called dot notation to describe velocity and acceleration, and that was a Newton notation. Yeah, so there's a little history lesson. So displacement, velocity and acceleration. Displacement, now those of you that are doing physics, how many people are doing physics, just out of interest? So what's that, about half of us? Physics tends to use S for displacement. We tend to use X, because we just imagine we're travelling along the X-axis, so we often use X. And so what displacement is, for those that don't do physics and maybe unfamiliar with the term, we talk about distance from a point, but with direction. So the plus and minus now means something different. It just says, well, to the left or to the right. It's got more meaning now. It tells the direction. Velocity. Well, velocity is the rate of change of displacement. So it's the derivative of displacement. So some notations for that. We could have V, obviously, for velocity. Newton's notation, the dot notation, is X with a dot on top. And then, of course, it's a derivative, so we could just call it dx to t. And as you can see, I put there, velocity is basically the speed it's travelling, but again, the plus or minus gives it some meaning. In which direction are you travelling at that speed? And then you have acceleration. And acceleration is the rate of change of velocity with respect to time. So some notations for that, obviously A for acceleration. Now, it's the rate of change of velocity, so it's the first derivative of velocity. So using Newton's notation, you could have V with a dot on top, or you could have X with two dots, because you've differentiated twice to get it. Or dv dt, the derivative of velocity with respect to time. And then there's this notation here, which we haven't really looked at yet, d2x to t2. It does not mean the derivative squared. Okay, that's not what that is saying. That's meaning what we call the second derivative, which means go and differentiate it again. So you just differentiate it twice. So when it comes to graphs, so we've got this displacement time graph there. Okay. Now we know that when the displacement graph is stationary, what should we be seeing on the velocity graph? Okay. Well, if it's stationary, the slope of that graph is 0. So on our velocity graph, we know it's 0. So we should end up with a, well, in this case, a t-intercept, because I've got time as my horizontal axis. That's why sometimes when I'm drawing these, I like to put them underneath each other, so I can just translate the information straight down. So velocity, bang, I know I've got the x-intercept, the t-intercept, I should say. All right. Well, there's another stationary point down here, so I know I've got another intercept there. Okay. Now, when the graph is increasing, we said that's when the derivative was positive. So from 0 up until that stationary point, it's increasing. So I know on my velocity graph, I should be positive. Now I'm not sure exactly where at this stage, but I know in that region there, the curve's positive, that new graph. And it's also going up on the right-hand side, so I also know my velocity graph will be positive over here on the right-hand side. And so similarly, when it's going down, so in between those two shaded areas, so it's decreasing at that point, so then on my velocity graph, my curve should be negative. So we're getting a bit of an idea of what this curve might look like. Now, the velocity graph will be stationary at that point there. How do I know that? It's when our displacement graph inflects. Okay? Now, an inflection point is when it changes what we call concavity. The most common, I guess, that we've seen already is with our cubic at the origin there. So that's when the curve's not reflecting, but it's inflecting. It's changing its concavity. So if I have a look at my displacement time graph, I've just estimated it to be around about here, is when it's changing from what we call concave down to concave up, then that must be where the turning point is on our velocity graph. Now, I don't know exactly how far down or far up. I'd need more information, so I've just estimated it there. Now, the same thing would happen when I'm trying to draw my acceleration graph. I could then read off my velocity graph and get information. So, bingo. The velocity graph is decreasing to this point, so I know it's negative. Velocity graph is increasing after that point, so I know the acceleration graph would be positive. We would have a t-intercept underneath our stationary point. Now, my guess on these is that first displacement graph, it looks like a cubic to me. It's got that cubic shape. And I also know that when I differentiate a cubic, I get a quadratic. So it's logical my velocity graph there would be a parabola. And when I differentiate a parabola or a quadratic, I get a linear function. So again, it's logical that I would have a straight line there. So that's other information I can look at when I'm trying to draw these particular graphs. All right, well, we'll have a go at 9J, which is using this idea of rates of change.